In this video, we will be deriving the capacitance of a parallel plate capacitor. A typical parallel plate capacitor will consist of two plates which are placed so close to each other, and you are going to create a charge by taking out some amount of charge from this sheet and you give it over here. Because these two are plates are like basically two-dimensional, and the charge density developed in this will be sigma. Sigma is the total charge you have taken out from this and give it over there. So sigma is actually equal to charge by area. Then if this sheet develops a positive charge density plus sigma, then the amount of charge taken and give it over there will be sigma into A. And because you have given whatever charge you have taken here and you give it over here, these two sheets have equal dimensions, then these two sheets will have equal amount of charge, but they are opposite in nature. If this develops plus sigma, this develops minus sigma, and the lines of force will traverse from positive charge density plate to negative charge density plate. And because you have taken out some charge and give it over here, electric field will be set up from left to right. Then the total capacitance, which we have seen in the previous video, capacitance is the ratio of charge to potential difference. And because the charge density is sigma, the charge is actually the quantity of charge taken will be equal to sigma into A. So this will be equal to sigma into A divided by the potential difference V. If you know the potential difference, we'll be able to, if you substitute the potential difference over there, we'll be able to find the capacitance of this parallel plate capacitor. If V is the potential difference between positive plate to negative plate, the potential difference between 2 points, by definition, it is a work done by the electric field from this point to this point, because you want, this is at higher potential, this is at lower potential. Potential difference is like work done by the electric field from here to here. But if you assume it is a work done by the external field, then it should be from here to here. If you have the distance of separation d, you have to move 1 coulomb of charge from this point to this point against the electric field. That is why the potential difference is integral of E dot dr with a negative sign. From where to where you are moving? From this plate to this plate against the electric field. That's why it is from d to 0. And one point you just need to remember is, if there is a positive plate, charge density is plus sigma, at any point on this plate or nearby any point, electric field is sigma by 2 epsilon naught. Because it is a positive plate, lines of force will move away from the sheet. Hence, it will be sigma by 2 epsilon naught to the right. Because of this, on this side, it will be sigma by 2 epsilon naught onto the left. But if you keep one more sheet of charge density minus sigma. Minus sigma means it's a negative plate. All the lines of force are coming toward the sheet. If this is the sheet, because of this sheet, there will be additional sigma by 2 epsilon naught electric field. Because it is negative, that electric field will be directed towards the sheet. Between the sheets, electric fields are like in the same direction. But because of this sheet, at this point, electric field will be in the opposite direction. So this sheet's electric field will be to the left, this sheet's electric field will be to the right. Hence, electric field on at a point outside the sheets will be 0. On this side also will be 0. Between the plates, it is sigma by 2 epsilon naught and sigma by 2 epsilon naught. They actually add to each other. Then the total electric field between the plates will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. It becomes sigma by epsilon naught. Then the potential difference V will be integral minus E will be sigma by epsilon naught into dr. From d to 0 we need to integrate it, and this will be minus sigma by epsilon naught. Integral dr is r, and where integration is from d to 0, then this will be equal to minus sigma by epsilon naught, upper limit minus lower limit, so it will be sigma d by epsilon naught. And V we have found out, and you know that what is the charge, the capacitance, which is equal to sigma A by V, but V is equal to sigma D by epsilon naught. Then the capacitance of a parallel plate capacitor is sigma A by sigma D by epsilon naught. Sigma and sigma will be cancelled. Then this will be equal to C is equal to epsilon naught A by D. So there is a distance of separation appearing, and A, area of the capacitor, is there, and epsilon naught is the permittivity of the medium. From this we get to know that the capacitance of a capacitor depends on the geometry of the capacitor. That means the length and breadth, also the distance of separation. So the capacitance of a material, or of a setup, is depending on the dimensions, the shape and the size of the capacitor, and also the material medium between the plates of the capacitor. Suppose in this whole setup, if you fill the entire gap with a material of dielectric medium, and the dielectric medium's permittivity is epsilon, then capacitance of a capacitor filled, parallel plate capacitor filled with the dielectric medium, C medium, will be equal to epsilon A by D. Then capacitance of a parallel plate capacitor with vacuum in between will be epsilon naught A by D, with the dielectric medium in between will be epsilon A by D. These two things you have to remember very carefully, because sometimes if you find the ratio, what is Cm by C, epsilon A by D by epsilon A by D, epsilon naught A by D. When you divide these two, what you will be getting is C medium by C vacuum will be equal to epsilon A by D by epsilon naught A by D. What you get is epsilon by epsilon naught, which is dielectric constant. If you want to find out the dielectric constant of the medium, all you need to do is just find the capacitance when the dielectric is filled and the capacitance of the vacuum. You will find the dielectric constant or relative permittivity.